Yeah, it's nice to be here. You know, it seems like it's a little bit easier for you guys to get people from Champaign up to visit you guys than it is for you to come. But if you're ever in the neighborhood, you know, have to get to Memphis, feel free to stop by. No, it's great to be here. You know, to part of the system to talk to you guys about some of the work that I've been doing. It's awesome to hear that I'm following up on a talk from last week that was also about embodied cognition. In some ways, it sort of takes the burden off me to do some of the intro stuff or to convince you that that cognition is embodied. If you were already exposed to that work. And so good introduction. I just want to mention a couple, I guess, sort of affiliations, give you an idea of sort of what I'm working on. So I run a lab that I call the Embodied and Immersive Technologies Lab, or the EMIT Lab, where I've got a bunch of students working on various aspects of design using ideas of embodiment, embodied cognition for the purposes of learning. And then just recently, I've taken over this initiative that we call Tier Ed, which is Technology Innovations in Educational Research and Design, which is meant to actually kind of go outside of the College of Education. See, we don't have, an LSRI down at UIUC, but we seek to do similar sorts of things in terms of interdisciplinarity. And so I'm trying to bring faculty members from engineering, applied health sciences, from art and design, from all these different areas together to really help work on these critical problems in education. And so that's now that I've gotten tenure, that's one of the things that I'm sort of the bigger picture things that I've been trying to focus on is how do you sort of make this interdisciplinary research happen. But I love being able to talk just about my work for a little bit, which I'll do now. So what I often do when I start these talks is I like to show this, what I think is a very provocative article. This came from Wired magazine. It's been a few years now, maybe 6 or 7 years ago, where the headline you see, "This machine guides your hand to teach you how to draw." I think this came somewhere out of Europe. So it's this device that they apparently prototyped that teaches you how to draw. Now, at one level, this is ludicrous, right? I mean, let's just get that off the table. So the idea that that this thing, I mean, maybe it could get you to draw a tree or a cow or some specific thing. The idea that it could actually instruct you to draw the way that an artist does is sort of impossible. But I wanna just suggest that there may actually be something here in terms of, because the truth is we do this in a lot of different domains. So we prompt and we encourage people's movements in fairly specific ways as the foundation for them to learn new things. So we don't often, particularly in very physical and practical domains, we don't often start off with, here's my verbal lecture about how to do this physical skill. It's, here, let me show you how to do this, and let me even guide you in the process of doing those things. So if you had a chance to read my cueing chapter, for example, I start off by talking about my daughter learning how to play piano, and how, one of the first things the instructor does is have her put her hands on top of the instructor's hands, just as a way to sort of get a feel for how this kinds of motion works. And I don't think that that's necessarily just good for learning the mechanical motions of playing the piano, but it also introduced her to being receptive to the ideas of music and music theory in addition to those physical skills. And so the provocative idea that I want to leave you with is not that we're going to have devices like this anytime soon, but that this notion of prompting specific movements, of eliciting actions that are commensurate with important ideas could be a good way to learn. And that's you're going to see this idea keep coming up in my talk today. So this is just kind of a breakdown of what I plan on talking about. basically just kind of slowly layering on ideas, and it's really just meant to be kind of a vehicle. A loose structure is a vehicle to show you some of the work that I do and some of the projects that some of the interfaces that we've created. So again, I don't think this is something I have to belabor for a long time, because I think I'm preaching to the converted here. But there has been really, I think a real shift within the last few decades into how we think about thinking, how we talk about cognition, and really recognizing the important role that perception and action and all sort of embodied interactions that we have in this world play in that process. There's been some wonderful, philosophical pieces. A colleague of mine was a colleague of mine at University of Central Florida. He's now at Memphis, wrote this great book, How the Body Shapes the Mind. Sean Gallagher, Andy Clark has done a number of books on this topic as well, and there's good empirical evidence, and those of us who work in this space, all have kind of our favorite studies, right? That sort of establish this idea that the mind and body is connected, and so I won't list any of those studies here, but studies showing that neurological studies, for example, showing the connections between the parts of the brain that are responsible for motor control and movement are tightly connected to the semantic meanings that go behind those actions. So the lick, kick, pick study, which is a popular one to cite, the idea that if you say those words lick, kick, and pick to somebody in a scanner, the parts of the brain that are responsible for each of those types of actions are going to be activated. And there's a number of studies that go even further than that, showing that somebody who has played hockey is going to have activation for in their brains when they're seeing or hearing descriptions of hockey action. So because of that expertise that they've developed, they're going to be particularly sensitive to those activations. So we're going to assume for the rest of this talk that there is this connection between embodiment and learning and thinking. And if it is the case that there is that connection, then I think there's also it follows that process of learning also rely on our physical interactions, and so we need to start thinking about the design implications of that. So yeah, I'm going to skip through some of this. So, but I do want to catalog some studies that do, I think, a really good job of just suggesting this connection between embodied action and learning, specifically the prompting of embodied action. So Susan Gold-Meadow has done some great work, a large body of work around gesture, but some of it has been specifically about, if we give people particular gestures to do, can that aid them in processes of learning? So this being one of my favorite studies, where the simply prompting a student to use this type of gesture to denote the two parts of an algebraic equation, and that they come together to form one sum, helps with their reasoning about these problems, and ultimately leads to higher performance. Similarly, there's been good work also out of the University of Chicago, I believe, where giving people motoric experiences or physical experiences with things like angular momentum. And this was also an fMRI study that actually showed that for people who had these kinds of physical experiences, if those areas of the brain that were activated when they experienced these things are activated on an assessment of these things, they tended to do higher on those areas of performance. So that's sort of showing the benefits of having these physical experiences and tying them to the concepts of even fairly abstract ideas like angular momentum. And then, just because I like to do something outside of STEM, I love the Art Glenberg work that showed that for reading comprehension, having students actually act out scenes of things that they have read, like a story about something happening on a farm, leads to higher comprehension of the passage that they read. And importantly, it doesn't even have to necessarily be the physical movement of these things. Even the imagined manipulation of these objects leads to that, to those effects as well, suggesting that even through imagistic reasoning, we are still recruiting our embodied our embodied action in our thinking and in our learning. So if we embrace embodied cognition, then it stands that there are some, I think, really compelling implications for educational design. And so one of these things would be saying that expanding one's repertoire of movement and physical activities has the potential to expand thinking. That's a pretty powerful statement, right? Just the idea that getting somebody to move in new and different ways, creates a platform for new learning. And there are people who are trying to make these connections, dancers and people in theater and people doing very physical things are experimenting with this. Like, are there ways to teach people ideas in physics through dance activities, et cetera, et cetera. It also, I think, suggests that learning interventions need to consider the type and the quality of interactions that students have with physical environment, and I think this is something that you probably are all sort of bought into, but this idea that it's what really matters is the information that's being presented, that the demonstration goes well, or that the diagrams are really good, is still very prevalent in our schools and other educational environments. And we're not necessarily thinking about what perspective are we giving people on those learning materials, how long and what kinds of physical interactions do they have with the things that they're seeing in those contexts. And so thinking about those quality questions when it comes to interactions, I think is really important. However, and hopefully I don't need to say this, it does not mean, and I don't believe that means that unconstrained physical activity will necessarily be accompanied by new learning. It's an important thing to say, because I think there are a lot of people, I have quite a few interactions with teachers in the classes that I teach, and there does tend to sometimes be this idea that, well, embodiment is good, so we should just do embodied stuff all the time, and that, if you get the juices flowing, or whatever the sort of cliched terms that people use, that will just naturally lead to more learning. And there really isn't evidence for that being the case. The studies that convince me that there's an embodied connection to learning are the ones that show that very specific types of movements that are commensurate and aligned with the concepts that we're trying to teach, that those are the things that tend to lead to more learning, not doing jumping jacks in between problem sets. And so now I want to talk a little specifically about science learning, and I like this quote from a friend of mine at the University of Edinburgh who works, he actually works more in the area of early math development, Andrew Manchez, but he gave this really nice, I thought, sort of definition that describes science learning. Embodied cognition is an umbrella term that refers to claims that the way we think is inseparably linked to our prior and current sensory and action experiences. This is significant for science learning. Sensory and action experiences do not simply engage children in science ideas, they are internalized and activated as an integral part of science concept development. And so that's kind of the basis with which I do most of my work, thinking about science concepts. But we have to acknowledge that embodied interactions do not automatically engender science learning. And we know this because we have lots of everyday experience with science, right? So we have lots of experience pushing and pulling, and yet we don't come out of those experiences with a firm idea of, say, kinematics. To cite Andy DeSessa, thinking about science knowledge as really being these weakly organized systems rather than these coherent theories of science. And And so certainly relying on these embodied, sort of precepts, these embodied primitives, but that does not engender the kinds of science learning that we want to see come out of our courses and our programs and the critical ideas that students need to understand. So there's some sort of intervention that needs to happen there, right, to bridge between those embodied experiences and to allow for the more robust learning that we want to see. And one approach is to bridge these embodied experiences to formal concepts through analogies and metaphors, and to provide opportunities for reflection on those experiences. So those are the two big things that I focus on. That it's not that an experience, riding in a car or throwing a ball is by itself going to engender science knowledge, but those things treated as metaphors for understanding, more sophisticated, understanding of physics can be really useful, particularly if it's paired with opportunities for reflection. And this is where I think that new digital interfaces can play a really important role, because unlike the ephemeral experiences of doing a gesture or having some sort of physical interaction with an object or another person, digital interfaces can capture those experiences, replay them, and allow you to repurpose and manipulate those representations in ways that can actually benefit learning. So now I want to talk a little bit about why embodiment and new technologies. So why are digital media technologies important to the space of embodied learning and science? So I think making metaphors salient is one thing. I think there's been a lot of work. Niebert, for example, wrote a paper recently about science education and about how a lot of the metaphors that we use in science education are really sort of inadequate, particularly given what kinds of experiences actual children have had, and also our sort of lack of ability of sort of appropriately making the connections between the source and the target domain for students who are trying to understand it. Whereas using technologies to support these metaphors gives you a lot of freedom to be able to reinforce the particular aspects of the metaphor that are important, right? So you can do things within technologies to slow things down or to make things salient that allow for metaphor making. Opportunities for reflection, so re-seeing in action that you made. I mean, I've already probably made about 1,000 or so gestures just since the beginning of this talk, but I can't easily remember or even recreate those gestures for you because they are ephemeral. But if through the technologies, recording devices, things that can easily play those things back, you can see those again, reflect on them, and make meaning out of those experiences. And then cueing, which was again sort of the focus of the chapter that was made available to you guys. This idea that digital interfaces, sometimes better than just sort of natural interfaces or other people, can do a really good job of prompting people to do specific actions. So we've got decades of research in human-computer interaction that is really kind of about this, right? Like, how do you effortlessly get people to make connections and understanding with computer interfaces such that they're able to do actions that are intuitive, to be able to accomplish goals that they set out to accomplish, to create these kinds of digitally mediated experiences. And we can use this now, I think, in the space of embodied interactions. We can do things within digital spaces, even immersive digital spaces, that can elicit the kinds of physical interactions that we want people to do, because we think that we've seen that they've been productive for new kinds of understanding. And so I'll show you some examples of some of the interfaces that we've created that do this. And I think that there's good there's a good psychological basis for this, and a lot of it comes from this area of attentional psychology. There's been years of research showing that it can be beneficial to help guide people's visual attention through some complicated space as a way of getting them to understand what matters, what are the important distinctions that need to be made. Even looking at the Chuck Goodwin work on professional vision, that shows that that the process of attaining expertise is really about being guided through the domain and being enculturated into what are the important things to look at, what are the important things to notice. And I think that a lot of that has parallels with embodied interaction, that we can also be guided in a very physical way through a space. That if you're interacting with an experiment or some object or artifact for the first time, just knowing sort of where to stand in position with that object, or how to hold that object in ways that's optimal for making the connections that somebody in that domain needs to make, can be a really valuable experience. I like this headline to this paper. I cite this paper a lot: eye movements and problem solving. But the key thing here: guiding attention guides thought. I mean, what a provocative, a statement, right? This idea that you can guide someone's thinking just by sort of guiding where they're looking in a domain. And again, I think we can do similar things with embodied interactions. And we kind of know this, right? Because video games are really good at doing this, right? So video games have this ability, because of what they are and what they need to be commercially successful. They have this ability of training you very quickly to do novel things with an environment that you're not familiar with, right? So they have all these conventions for getting you to do, ghosting and other types of cues in these environments, to get you to do things and to feel competent about the actions that you're taking in that environment very quickly. Because if you don't, if anybody who plays video games knows, if you play one for more than 10, 15 minutes and you don't feel competent in that game, you're going to put it down and you're never going to play it again. So they have to develop these techniques. But these are techniques that for whatever reason, we don't often use in educational environments. We don't use in the design of new technologies. And I think that it's time that we start looking at those spaces and figuring out what can we borrow, what can we steal in this environment. But remember, just like unmediated embodied experiences, not all embodied technologies are effective at generating new learning. So, I mean, there's a lot of examples of this, and I always feel bad picking on one in particular. But this is a Kinect game, for example. I don't know how well you can see this, but it's a soccer game, and so they're doing kicking movements that are recognized by the Kinect that they're playing with. And the purpose of the kicking is to select the answer to a math question that has been presented on the field. And I mean, obviously, why on earth would that be a better way to answer an arithmetic question?
It'd be a great way to run a math classroom.
Yes, I know. Just the sheer spectacle of everybody putting their legs up in the air just to answer a multiple choice question is hilarious.
I don't know what you guys do in your classes. That's what we do.
And unfortunately, there are quite a few examples of this out here, and it's not just related or just in the commercial sector. There are research studies that are being done on these kinds of interfaces where the embodiment is really just sort of a means to doing fairly traditional learning environment operations. I mean, we discussed this some this morning. And so we need to be vigilant about that, and we need to be vigilant about why embodiment matters in these kinds of environments, and what are the particular ways of creating those positive interactions. And so so creating meaningful mappings onto the concepts and ideas is a really important thing to do, and it's hard work to do. I mean, it's not always obvious what are the what are the potential metaphors that can be made. Another thing we talked a lot about this morning is that we've got these kind of pathetic bodies for the purposes of making physical metaphors, right? I mean, we're pretty limited. We've only got arms that are so long. We've only got 2 of them. We can only do so many things. But with these new technology environments, we have this opportunity of expanding that space. So I don't just have to be this pathetic body with 2 arms and 2 legs. I can be this, this instrument that works along with a digital interface that can create, universes or interact with molecules. I mean, do all these augmented things that are still physical, they're still embodied, but they are metaphor building tools as opposed to just what you can do with actual physical manipulatives. So now I'm going to talk about some of the projects that I've been working on over the past a few years, and it's all meant to be. And I'm just going to kind of go through some of these slides, show some videos. Please, I should have said this earlier, please stop me and ask questions about these things. If I don't get through all of them, it's not that big of a deal. I'd much rather answer your questions. It's all meant to sort of, without really being very deliberate about it, to sort of suggest what are some of the design principles that go behind creating these environments. And that's the great and exciting thing about this space that we're in right now, is that we're finally at the stage where we've got people, myself, we've also got Dean and Mike, who wrote a great paper last year on this topic, and others that are starting to articulate, well, what are the good principles for designing embodied learning spaces for STEM, for topics in general, that we think are going to be effective and can be guidelines for people who are in this design space. Because not everybody who's creating these technologies are going to be learning scientists. I mean, let's just be realistic about that. I mean, there are a lot of people who have gotten very excited about the prospect of changing up education, and so they'll undertake these things without the real understanding of what makes a successful embodied learning space. So the first one that I'll talk about here, which is kind of was sort of my first foray into embodied interactions in a sort of big immersive space, was this Meteor project. And I actually did this project when I was at the University of Central Florida prior to my current position. And at UCF there was this great Institute for Simulation and Training where they had the resources to be able to build these great immersive environments. And so we worked on this project that NSF funded, where we created a large simulation that was really just meant to get middle school students to understand basic ideas, develop intuitive notions of basic ideas of how objects move in space. So, Newton's laws, Kepler's laws. And they did this by basically interacting on this large 30-foot by 10-foot platform of projected imagery that was down on the floor. But through laser scanning, we didn't have a Kinect back then. This is pre-Kinect. It was a laser scanning technology. We were able to track where the student was in this space and be able to allow them to make predictions about where this asteroid that they were launching into this field was going to move with other objects like planets that have gravitational forces acting on it. And so they went through these different levels, making these predictions about these objects and getting real-time feedback about those predictions. And so this is a real quick clip. This is actually a version of the simulation that has him loading up his asteroid in a spring launcher. This allows him to basically vary how much force is given, how much initial velocity is given to the asteroid, as well as setting what position in the horizontal plane that he's going to set it on. And so his goal is to hit this red target But you can see here you've got this big old planet that's right there. And so you're going to see him sort of iterate on this. And yeah, let's watch what happens. So his job is to basically track and predict where that asteroid is going to go. And so he launched it initially, and I don't think he even really saw that it sort of swung around the planet there. So now he's going to do it again, and he's basically going to do the same thing that he did before, but he's going to be watching a little bit more closely. So he missed again, but now he knows he missed, and he sees where it went. And so now he's going to make an adjustment. Over here, and this time he's going to get the position just about right, but he doesn't quite get the speed yet, and the fact that there's gravitational acceleration. So most students at this stage assume that they're moving at uniform speed as they're going around a planet or by a planet. And so now he's going to be a little bit more aware of it. At the target there at the end. And so, he goes through these different iterations, and, I'm not saying that he comes out of this with, a full idea of Newton's laws, but certainly has developed some intuitions about it. Yes?
That's a question. So when he's at the little thing, so it's kind of like a pinball machine where he's pulling back, and the level that he pulls back is the amount of speed that he's
Yeah, so that just changes the initial velocity.
And so then when he's running, is he following the thing, or is the thing following him?
So he's actually following the thing. So what he gets to do is he gets to set the initial position.
It up, and then he follows the rest of it.
Exactly.
Okay.
And then the rest of it is him making predictions about where.
Got it.
Where
after he leaves that little mark, he's no longer in control of the thing that he was on. Okay.
Right. And this is a theme that you'll see throughout the projects that I'll show, that what we like to do is we like to mess a little bit with this idea of who's in control. And you can do some kind of, I think, neat things with that. I mean, it can be frustrating too sometimes. I'm not saying that everybody who went through this, got it right away or wasn't frustrated by it. But you can get people into situations that I think are advantageous for making conceptual advances, which is what we want. I think if I'll show this just because it's a little bit entertaining. So this is her trying to put an object in orbit, which she's done, but realizing that it doesn't move 2 times around in order to show that you got it in the path around. Realizing that it doesn't move uniformly is something that I think surprises her a little bit. And so you're sort of shuffling around to do that. All right, so the other paper that I made available to you guys was actually a paper that does some empirical, or basically does a study to compare whether or not this type of interacting with these ideas is better than a desktop version of the same simulation. So same tasks, except now I'm using a mouse and using that to control my trials and my predictions. And if you were able to read the paper, you'd see the findings were good on multiple fronts. We found effects for learning in terms of just general physics ideas. We found good learning results in terms of relevant ideas of how objects move in space. And we also found positive effects just in terms of science self-efficacy and feeling like they had learned something through the process. So that was good, and I think it provided a nice sort of initial study that has allowed us to do more sort of sophisticated work since then, because it showed that there's just something there's something initially good. We don't necessarily know exactly how to describe it, but there's something good about engaging the body in these kinds of prediction-making activities that seem to lead to conceptual development, at least compared to just operating it through a mouse control. But the disadvantage of this kind of environment, well, it's not really a disadvantage, but I think the limitation of it is that this is an embodied metaphor that's fairly literal, right? It's a fairly straightforward. My body moving stands for an asteroid that's moving, and I'm learning about the way objects move through that process. And we've really tried since then to think about ways to engender more sophisticated kinds of science understanding through these embodied interactions. If embodiment is going to be good for embodied interaction is going to be good for learning, gosh, it better be better than just learning about how things move, right? Or things that are very easily associated with body movement. And so what we've been doing since then is looking more at things, more sophisticated things like science explanations. Like, can you incorporate embodied interactions in ways that improve students' abilities to create good explanations of science phenomena? And so I want to tell you quickly the story of Jada, who was an initial participant in this much longer set of corpus of research that we've done. But we were interested in her explanations. She's a middle school student. Her explanations of gas pressure and the causes of gas pressure. And the way that we framed it for Jada was that we handed her one of these plastic syringes, and just these cheap things you can buy at like Walgreens, and we actually melted the end of it so you couldn't actually get any air through the end of that syringe. And we asked her two questions. We said, what's going to happen when you try to push in that syringe? Because it had this much sort of air in it, and then what will happen when you let go of that? And initially, she really struggled with this. I don't believe her initial predictions were correct. Just in case you're wondering, the correct answer is that you can push it in partially, not all the way, and then when you let go, the piston goes back to the initial position. And so the question is why? Why does that happen? And Jada was clearly kind of on that sort of middle space between having a particulate view of matter and not having that view. But she knew what molecules were. When we pressed her a little bit, she seemed to understand that air was composed of molecules. But the moment in the interview that it really seemed to take hold for her was when we were asking her, well, tell us about these molecules. What are those molecules doing inside of that container? And she started to represent the molecules with the fingers of one hand, and then the wall of the syringe with the other hand. And she started representing the tapping of those molecules against the container. And when we asked her, well, what does a high pressure situation look like, she'd start increasing the frequency with which she was tapping her fingers. And then a low pressure situation was sort of a slower hitting of the molecules, which is really what we're trying to get at, right? That causal mechanism here is the frequency with which those molecules, all other things held equal, it's the frequency with which those molecules are hitting that syringe, and those little collisions add up to the big collision that pushes back the piston. And so that interview was really inspiring for us in the sense of we can take that embodied action, that hitting of the fingers against the hand, and seed that to other students who are having a hard time understanding this idea, and possibly promoting greater understanding of these topics in that way. But what we also realized is that it wasn't for Jada, she came up with that on her own, and it was really that prompt to, can you just show us what you're thinking about this, that led her to create those representations with her hands. And so we actually looked at this across a number of different areas where we had kids give initial explanations of these ideas in 3 areas: gas pressure, heat transfer, basically why does the handle of a metal spoon get hot when you dip the bowl of the spoon in hot water, which is another idea that students often struggle with, and then the causes of seasons. And so we asked them these initial explanations, and then the intervention was very simple. We said, can you show us, show us what you mean? And if necessary, we prompted them to use their hands, but we almost never had to do that. I mean, without any paper or pencil or any other resources available to them, if you say, show me, they tend to use their hands as a way to represent them. And that simple prompt to have them show us led to explanations that had more mechanistic elements to them compared to the initial explanations that often did not. And so, it was really, I think, just a good demonstration and a good rationale for our future work that would try to explicitly prompt them to do not only these actions, but in some cases more specific physical actions to represent it. Oh, I did want to show this video clip because I think, so the question is what exactly is changing about these explanations pre and post prompt? And I think this is a good example where, it isn't even necessarily that her explanation is that much better after as it is before, but you can tell that her whole perspective on how she is presenting the answer changes. So let me play this for you, and you can also see the transcript on the screen.
Angle in the winter so we get the light and heat less intensely. Does that make sense?
Yeah, I think that makes sense. And I'll ask one more time, but this time, could you show me somehow, like with your hands maybe, what you're talking about as you describe it?
Like, so this fist is the earth and it's upright is like this, but it's kind of tilted normally.
Okay.
So the sun is always shining like this, but it's going out like a spotlight, is stronger in the center and it fades more when it gets towards the outer sides of the circle. Mm-hmm. So it would go, when the earth turns, it goes around the earth like this, and the angle that it's at doesn't change. Mm-hmm. So if it's here and we're here, mm-hmm. it would be less intense than if we were here.
So you can see that, in the second explanation, she's kind of taking a different perspective. She's thinking more almost as her being the sun sort of emitting these rays. And I think it seems like that's allowing her to think about, this density issue, the density of the rays that are hitting a particular part of the Earth, better than when she was focusing more on the Earth's perspective and thinking about this issue of tilt. I mean, some of you may have had this phenomenon before that when you ask a kid, well, what causes the seasons, they almost shout tilt of the Earth at you, and sometimes they'll even give you the degrees of the tilt. But that often doesn't translate to a real understanding of what actually is going on in terms of the spread of the light rays that is causing the seasons. So we thought, even if you don't necessarily think this is a better explanation than the other one, just the prompt to show us what she meant changed her perspective, and I think allowed her to think about the problem in a different way than she had initially. So again, this has really been the impetus behind this our GRASS project, which is a collaboration with the Concord Consortium out in Massachusetts. And we've been creating simulations around these 3 topics that allow for hand gesture interaction with these three sets of phenomena. And we use the leap motion, and so I'll show a video here that'll just kind of go through while I'm talking. We use the leap motion to read the students' hand gestures. You can see that initially it actually shows them exactly what their hands look like on the screen. But once they start doing the thing that they're supposed to be doing as a way to enact the simulation, the hands go away. So it's sort of a way of fading, because we don't want the hands to always be in front of them distracting them. And so this is the gas pressure simulation. You can see we have the Jada move of having the hands hitting the side of the container. The leap isn't great at fingers, so we couldn't quite do exactly what Jada did, but I think we at least captured the spirit of it. This is the season simulation showing the angle of the light rays as they hit the Earth. So you can see that as you change the angle here, you get more or less concentration, and that allows them to actually count the number of rays in one position versus the other. This is our heat transfer simulation, which really focuses them on the idea of collisions of molecules and the chain reaction of molecules that would go through, say, a metal spoon to heat up the end of it. Yes.
So in all of these, are they controlling, so the one I was specifically interested in was the one where the thing was moving and the particles were moving?
Yep.
Were they controlling two things, or were they imitating one thing and controlling
So they were
another?
controlling the speed or the frequency with which the molecules were hitting the side of the container. So what you may have actually noticed is that as I do this faster, the plunger is actually going the opposite direction than I'm pushing, which is one of these sort of like messing with control sort of situations, right? So the assumption, because this is how most educational simulations work, is that they're going to be controlling the syringe, and they're going to be pushing it in the direction that the syringe is going. And that's all fine and good, but that doesn't really get them to think about the causal mechanisms behind gas pressure, right? And so what this does is it, I think, creates these situations of dissonance, which some of the kids are very open about. They're like, wow, I really expected it to go the other way, but I see that as I increase this, it's actually going the other direction. And if you keep sort of interacting with them on that, I think they start to sort of recognize, why that is the case, and they end up giving some pretty nice explanations of the science behind it. But even you can make the same argument with the season simulation. I mean, it's a little bit strange for them to be thinking of it at the level of the angle of the light rays, right? Because it's almost flipping the causality. But again, it gets them to think about that the density of those rays hitting the surface of the Earth rather than just the macro phenomenon of the Earth's tilt. Okay, so we're 153. Keep asking questions as they come up, but I do want to talk about then go on to the next project, which is the elastics project. So this is kind of yes, Mike.
If you're about to switch projects,
Yes.
I want to ask about
Please.
the causality problem.
Yep.
So you just said exactly what I was worried about, that the causality has been flipped. And so just to make sure I understand the interface, when they indicate that the particle should be speeding up, the simulation responds by moving the plunger in?
Yes.
Which is exactly the opposite of what happens.
Well, I mean, it depends on how you look at it. So they're not, I mean, it is what happens that there's actually more pressure, right, happening within inside the container.
But the causal explanation for that is an external force has been applied to the system, reducing the volume, therefore increasing the number the number of collisions between the particles and the walls. So that may
right.
What? So I mean, have you analyzed?
But they're not explaining the force that the thumb is putting on the syringe. What they're explaining is the internal pressure of that syringe.
But so none of them are saying, as the number of collisions per unit area increases, that pulls the syringe, the plunger in.
I mean, not with our simulation.
Nobody said that.
They're not. No. No, I mean they're well. So I mean I don't know if you saw there's a pressure bar
On the right.
that right on the right that's showing basically and it's connected with the number of molecular impacts that are happening. So the more of those that occur, the higher that bar goes. So they see that connection. So as their hand increases, the number of red collisions go up, the bar goes up. So they see that connection.
But you could have chosen a design in which it was a fixed piston, and they could have increased the number of collisions, and the same pressure result would happen with the fixed volume.
Right, but there's not a easy analog to this type of thing that they can connect to, right?
Yep.
So the idea was not to separate it completely from the phenomenon of the syringe. We wanted them to still think about those syringe, but it's really just sort of a flipping of the question. Like we wanted them to think about what's happening inside of that syringe, not be thinking about your thumb. And so after they've had that initial experience with pushing it in, we take that away and then we give them the simulation that they're allowed to interact with. But the question is always about what is causing the pressure, not what's causing the syringe to go in the first place.
Okay.
So I was going to ask about what questions you ask them afterwards, because I think how you frame those questions would definitely affect whether they're going to ask about or deal with this plunger. So they actually interacted with the plunger before you gave them the simulation as well?
Yes. So
Okay.
they had a chance to
So
try
they've
that.
seen that it's actually they have to push in, and then you're looking
Yeah.
at.
Yeah.
Hmm.
Yeah, and there have been plenty of debates even within our team about what is the right way to sort of set up these situations. But what I can be fairly confident of is that simply giving them what we call the phenomenon control instead of the explanatory control.
Yeah, that's it.
It doesn't really lead to the kinds of science explanations that we really want students to produce, because they're thinking about this pushing, the pushing that they can feel. And they've even Concord Consortium, I think, had one of these simulations where they'd push a physical syringe and they'd see a digital version of that in. But it seems to be a difficult leap for students to get to that mechanistic reasoning.
It's cool the way that you're playing with controlled here. It's really you said exactly where I was trying to catch up to you on that, which is that they're gesturing how they would explain it, right? They're gesturing the explanation, and the way that kids often interact. In fact, we've done it with a planetary orbit simulation with the interactive physics. We've done it with the tilt of the Earth and the rotation, and if they see a simulation where they do something and it explains it to them, they go, "Oh, okay, I got it."
Yeah.
And it's not embodied, for one thing, and it's not explanatory. They're being explained to.
Right.
So I don't know how to apply this in other ways, but the causation correlation problem, it seems like you're going at it from a really interesting way.
Yeah. Well, even with the seasons, I mean it's hard to know exactly what's all happening here, but so many kids, even after instruction on this topic, still come away with the distance idea,
Not just
right?
kids.
That it's the distance between the sun and the Earth, and I think it's because they're focused on the sun is this heat source, and so I mean the obvious thing is just how close you are to that heat source, because if I'm close to a campfire, I'm going to be warmer than if I'm farther away from that
embodied,
that campfire, right? But it's a misapplication of embodied experience to this problem, and so we're trying to kind of shake that up and try to bring in embodied experiences that are relevant, and thinking about angle and the resulting density of sun rays as a result of that angle has been our initial approach, at least to do it. Yeah.
One of the things you mentioned at the beginning was that where I just sort of focus on metaphor and analogy and then reflection. Can you talk a little bit about how you, what sorts of designs you have for or what do reflection opportunities look like for
That is a
kids?
great segue into my next
Excellent.
my next
All right.
project. If I can do that, I mean, it'll take me a minute or two to get there, but so continuing in this theme of trying to make these embodied interactions meaningful for more abstract ideas. We come to our next project, which is trying to figure out how can embodiment support things like the cross-cutting ideas in the MGSS. These big ideas in science. These things that are honestly hard for students to grapple with, particularly to grapple with them across domains. So you may learn about nonlinear scales in physics, and then you'll learn about it again in chemistry, but there really is no exchange in between those ideas, even though it's the same ideas that are underlying both of them. And so our thought was, are there ways to really ground these in embodied actions such that they can fairly easily be transferred across the areas? And so our solution, which you'll see in a second, is to kind of create a sort of reflection space for that. But I just want to start off with this example. In pretty much all my projects, we never leap right into creating the technology. We always try to understand, well, what are the sort of intuitive, embodied ways that students understand these things. And this was us talking to this student about what does it mean to double something? What does it mean to double a quantity? Because we're trying to get into this idea of scale. And what we found, a number of our students doing is that they would come up with some metaphor of objects where you were stacking an object on top of each other, or folding objects such that you go from 1 to 2, or perhaps 1 to 10 in the case of like a base 10 scale. And this is not to say that all students immediately went to these metaphors, right? I mean, sometimes you'd ask for what does doubling mean, and can you show us that with your hands? They'd do things like this, right? Giving you a very symbolic way of doing it. But what we found is that the students who did more metaphorical types of things tended to do better on the more advanced, reasoning types of problems than the students who were kind of stuck in these sort of symbolic modes of thinking about number. And so, what we've tried to do on the Elastics project is to create these science simulations that have this common scheme for representing ideas that are grounded in these cross-cutting concepts. So initially, it was this concept of scale. And so I'll show you sort of what this looks like. So what you see here is you see students using their body to communicate about ideas of scale. I'll talk through this instead of listening to my recorded voice talking about it. So this is a student. Basically, she's been trained. The system has been trained on her ways of representing ideas of scale. And so we asked her, how do you think about multiplication, and kind of prompting her to do these gestures that represent multiplication as opposed to more additive types of gestures, like taking an object and moving it to a pile, and then gave that as seeded that as a way to interact with these science phenomena. So that just kind of shows what our setup looks like. It's like 3 screens. They're standing in the middle of them, and they're using their bodies, full bodies. They can use legs as well as arms to interact with these things. And here's what the actual simulations look like. So first we give them a play space for just sort of getting comfortable with this type of motion, for example, being multiplication, this type of motion being addition, and then we give them these simulations. So this is earthquakes. So this is a simulation where they are essentially creating earthquakes of different magnitudes that they then trigger and watch the effects of that earthquake on a nearby city. Sorry. So, there we go. So they see themselves. So here's some reflection there, right? You can see you can see themselves as they're performing these gestures, and they're scaling this up. So they're creating an earthquake of a higher magnitude. They're also getting the amplitude, and so they're seeing this relationship here, right? It's a relationship where, you know, the distance, for example, between 4 and 5 is much larger than, you know, the distance even from 0 to 4, which is a really difficult thing for kids to understand. We always ask them questions like, you know, what is bigger, the change between a 7 and 8 or a change between like a 2 and a 7? And I mean, almost without fail, they'll say a 2 and a 7 is a bigger difference than a 7 and an 8. And so they learn a little bit about earthquakes, you know, the shift in the plates. They see the different waves go through, the S and the P waves, probably love waves coming through here. They see the damage caused to the city. And so they go through a set of problems where they're reasoning about these things. Everything that they're doing, every interaction with the simulation is with their body. They're not doing any other types of interactions. And then, you know, we do pre and post interview around these topics, try to find out how much they learned. And then a couple weeks later, we bring them back and we have them do a different simulation with the same scheme, but now we are doing acids and bases. And so we're doing still a logarithmic scale, but it is a different topic. And we're looking at whether or not success in the earlier simulation will affect their success in the acids and bases simulation a couple of weeks later. And drum roll, these are actually results that are just coming out now, but it does help. So students who do sort of a non-embodied learning of the earthquakes topic and then come to this pH topic do worse than students who started off with the earthquakes topic in the simulated mode or in the embodied mode and come to the embodied mode for the pH topic. And this is not just on in-game, you know, assessments of their knowledge. This is you know, just questions about these topics afterwards. So this is you're watching the effects on a pond ecosystem.
How are the non-embodied students being taught about logarithmic scale?
Yeah, so we've got a number of pretty high quality video as well as text materials that sort of instruct them on these same topics. You could actually make an argument that those topics are more comprehensive than this is. Yeah.
Oh no!
Sorry. You know, it's always a difficult question to find. You know, what exactly is the right control condition for these types of things. But like I said, you know, we worked pretty hard to find materials that covered the same topics, that give them the same information. But the embodied interaction and having the previous experience with the embodied scheme seems to do better. Yep.
At the very beginning, you were talking about unconstrained physical activity that doesn't really increase learning.
Yep.
I was wondering, because there's a lot of research that actually said that we need to get the kids out of the class to go crazy and then bring them back that actually will learn better.
Yeah.
I'm just wondering if that was something that, because it increased plasticity of your brain and the endorphins and everything else makes you a little more concentrated.
Yeah, there's a lot of links in that chain, and I'm not saying that isn't true, but I think I haven't seen, you know, entirely convincing research that convinces me that there's a direct connection between just pure unadulterated, you know, physical activity and then just doing better on whatever learning activity you get presented. And I am not against exercise. I mean, sometimes people, interpret this as I just want to put people in these like simulations and leave them there for hours. I think it's great for students to move around. I just want to be cautious in the interpretation that you're going to send a kid out to recess and come back and they're just going to be they're going to do better on learning specific ideas. I mean, might they be more focused? Might they have a better attention, or possibly, and that's great. And so yes, we should certainly have recess. But I would hate for that to be sort of the sole, design principle for learning environments, right? I think we can get more bang for our buck if we think about, well, what is this domain really? What are we really trying to get them to understand, and what are the best metaphors for that idea that's already embedded in their physicality, that they're moving around. So maybe it is even having kids go out to recess and then asking them what did you do on the playground today, and using those experiences as an opportunity for talking about whatever ideas. And although this has been entirely about STEM, I actually think that there's possibilities for this in other domains as well. I've got students who are social studies teachers, for example, that use this as a way to talk about different styles of government and social justice issues and things of that sort. I think there's just a lot of rich material in these kinds of interactions. So I just want to preview a little bit what we're doing now. So we're taking the elastic simulations. The one disadvantage of them is that it's just one student. And so we're actually creating ones, the Connect can recognize multiple people simultaneously. That's not a problem. So we've got simulations now where we're doing a new cross-cutting concept. We're focusing on rates of change. And we're having students, two students at a time, interact with a simulation that involves simultaneous rate manipulation. So the first one is right here. You can see we've got it's basically a population dynamics simulation. So it's sort of the classic sheep and wolves and plants. And so this student here is controlling basically the rate in which plants are introduced into the scene. This student is controlling the rate in which wolves are introduced into the scene. And in the center screen, which neither of them have total or direct control over, is the population of sheep. Sheep just disappear when they're eaten. There's no carnage involved. It's, yeah, I know, it's a little disappointing. And so what's kind of interesting is that in our pilot work with this, you can almost watch the change in their attention starting from the side. So on the very sides is where their skeleton is being represented. This is a graphical representation of plants. This is a graphical representation of wolves. And this is a graphical representation of the population of sheep. And as the experience goes on, you can just almost see their attention slowly go towards the center, right? The representation that neither of them are directly under control of. And we think that's a really sort of powerful way of setting up a in some sense collaborative learning environment where you start off in control of your own quantity, but you get them to coordinate on this, and I think through that process really understand sort of the nature of rates. And then we've got the same thing that we've developed for a basic climate change simulation. So controlling, how much CO2 is being put in the air by how many factories are on the ground, and then using tree production as sort of a proxy for reconsuming that CO2 into the earth, and then they see the overall effect of that here, and there's even like a nice ice cap representation that recedes and goes back and forth.
But in the game, you can hit start over.
So yes,
That's the big
yes,
difference,
yes,
right?
that is the
Mhm.
difference between there. So the last area, which I don't actually really need to talk about it. I just was going to show some examples of these kinds of technologies used in more informal spaces, because a lot of my work is actually done in museums and informal environments. So we put Meteor. This is at the Orlando Science Center. We've also worked with the Children's Museum in Indianapolis. You can kind of see in the image here. So this is another two-player experience that we actually brought out to the Children's Museum. It's a simple game. It's actually for elementary school kids. What's unique about it, here's another messing with control thing. This is two kids controlling one avatar. So this is two kids building up energy in different forms and then expending that energy to accomplish the goals within the simulation. So here they're doing sort of like eating motions to give robot food, and then using the robot to punch through a wall and do different tasks. There's some kind of, I think, clever things in there. So like they crunch down like a spring in order to gain potential energy that they can then use to do other tasks in the environment. It's really just meant to sort of develop ideas that energy is conserved and energy can be transformed. But it's done through this, I think, kind of interesting game mechanic. And this is we haven't done any lab studies with this. This is purely just something that we took out into the museum spaces. The last thing, I'll just plug this project that I'm on. I'm part of this larger network of universities and museums that are trying to understand, do a better job of understanding how young children, even preschool children's understand or embodied movements in those spaces interact with their science understanding. So even things like understanding basic ideas of like the scientific method of collecting data and setting thresholds and things of that sort through their embodied interactions.